having an effect on a consumer. Shimero responded to this kind of argument as, okay, yes, you can tell a representational story, but it is in fact a misguided effort because it totally goes away as soon as one starts to give the mathematical kind of account that Van Gelder emphasized, drawn from Maxwell's work. We're not actually learning anything from the representational account. Well, one reason to think that is it's not obvious where in here one's carrying there's anything that's representing, say, the speed of the flywheel. Not obvious, but Kel Nelson said, well, this is a good way to see whether it's there or not. Let's take this equation and solve it for the speed of the engine. When you do that, one figures out, well, there is things in the behavior of the angle arms that does in fact represent the speed of the engine. It's actually not the angle of the angle arms alone, although that is a component of the representation, but it's also the change of the first derivative of the angle and the second derivative of the angle. But put in this way, one then sees, okay, there are representations in the Watt governor. In fact, they aren't what we might have assumed. They're much more interesting than what we assumed because they do in fact carry information not about just instantaneous phenomena, but change in that phenomena. But when one puts the problem this way, one begins to see again what I'm driving at. Dynamical analysis and a representational analysis are compatible. And if you think about it, Watt governor is itself is a mechanism with parts and operations, and what we're doing is we're taking the dynamical representation of its behavior and using that to figure out things like how it is that the parts are achieving the objectives within the governor. Okay, so let me shift gears in this section now to turn to some work that's developed over the 20th century, but was largely ignored for much of the 20th century, but has started to become highly central, and that is way people are thinking of brains not as reactive systems, but as endogenously active systems. The contrast is actually seen between pioneer in neuroscience in the 20th century, Charles Scott Sherrington, and one of the people who was working with him, working in his laboratory, Thomas Graham Brown. Sherrington, for the most part, characterized sensory process, mental brain activity as beginning with a sensory input, a sequence of neural processes culminating in motor behavior. The very picture of a sequential operation of a mechanism that I offered earlier. Brown, who was working with isolated spinal cords from cats, found that they continued to generate patterns of activity, much like those in cats that were actually generating motor activity in response to a stimulus. But they were generating this activity even when they were cut off from inputs. And so he began to think that we should be thinking about the nervous system, ultimately the mind, as not just driven by stimuli in the environment, but as endogenously active. And we then should think of stimuli not as driving the system, but as perturbations to which the system will adjust through its ongoing dynamics. Within the 20th century, from a variety of sources, we began to get evidence that Brown was in fact right about this. That there are, for instance, in many organisms what are called central pattern generators, which are responsible for ongoing movement. They can be perturbed in the ways he was characterizing. But trying to actually figure this out at the level of brain processes took a fair amount of work. Most of the time, Rodolfo Linus was one of the people who focused on the kinds of things Brown was looking at, but he was doing it with single cell reporting. And what he was finding was that calcium conductances seemed to be varying in the cells he was looking at. He was looking at cells in the inferior olive. And what he argued was that the nature of these continuous variations in the conductances actually was capable of generating self-sustained rhythmic firing independent of synaptic input. So Linus's work, particularly in the 80s, but into the 90s and into this decade, has been one source of focus on endogenous activity. Even before that, Hans Berger's initial work with the development of the electroencephalogram, one of the first things he did was record from people while they were awake with their eyes closed, and found what he characterized as alpha rhythms of roughly 8 to 12 hertz that are ongoing in a resting brain. Now, he also contrasted that with what happens when a task is given to the subject, or the subject just is paying attention to things in their environment, and then he observed what he called beta rhythms, rhythms more in the 14 to 20 hertz range, but here again, evidence of endogenous activity. And I will focus in particular on work that's come out in the last few years on doing fMRI studies in the resting state, much like the state Berger was dealing with, where a subject is sitting in the scanner, just told, stay awake, do whatever you do, and images are made. Now, I want to contrast all three of these approaches with single-cell recording, EEG, or neuroimaging, with the more standard ways these techniques are used. So single-cell recording has most famously been used by, starting much earlier, but major breakthroughs with Stephen Kuffler's work, where what you do is try to figure out what kinds of stimuli will produce activity, drive activity here in cells in the retina or the LGN. Hugo and Wiesel's work on identifying stimuli that will drive cells in area 17, primary visual cortex, and that led to a 20-30-year success of unpacking ever more areas in the visual cortex. A lot of that I've reviewed in mental mechanisms, but the strategy there is provide a stimulus and record from the brain when the stimulus, as the person is processing the stimulus, comparing that against what the person would have been doing in other conditions. EEG has typically not been used in the way Berger initially started, but in terms of evoked response potentials, where one time locks the EEG to the presentation of the stimulus so as to decipher patterns in the response to this stimulus. N100 waves, P300 waves, whatever. But again, it's as treating the brain as a reactive system. And PET and fMRI have been used in much the same mode. Present a task to the subject, say the Peterson et al.'s verb generate task, where subjects either saw a word and read the word, or saw the word and generated a verb to go with the word. And what one's doing is then looking at the specific brain response to the presentation of the task. This is what I'm characterizing as the reactive approach, looking at the brain as how it reacts to the stimulus, as contrasted to the endogenous activity approach, active approach, looking at the activity that's going on in the system when it's not being driven. Well, let me say something about what kind of evidence is coming forward as people have done this now in the context of neuroimaging. One of the things that actually led to this was Gordon Schulman and his collaborators in the Reiko lab noticing that in a whole host of tasks, there were a set of areas that seemed to decrease their activity as the person was performing the task, not increasing. So they seemed to be areas that were most active when the person was in the contrast state, not in the active state. Areas that included the posterior cingulate cortex, the precuneus, inferior parietal cortex, areas that are showing up in this map. Notice, unlike many neuroimaging maps, these are decreased activations showing up in red. These are areas that seem to go down in activity on the occurrence of many tasks. Reiko, in a paper a decade ago, started to move to characterizing these areas as constituting a network. We emphasize this consistency with which certain areas of the brain participate in these decreases made us wonder whether there might be an organized mode of brain function that is present, as he was doing at the time, taught at the time, as a baseline or default state, and is